Now that we know how to determine whether a function is continuous, let's look at the different types of discontinuities that can occur when a function is not continuous. The first type is called a removable discontinuity. This happens when the limit exists, but the function value is either missing or different from the limit. Visually, this looks like an open hole on the graph. The graph approaches certain value, but the function is either not defined there or the point is placed somewhere else. It's called removable because we could fix the discontinuity simply by redefining the function at that point. The second type is called a jump discontinuity. In this case, the left-hand limit and the right-hand limit both exist, but they're not equal. So as we approach the point from the left and from the right, the function approaches two different values. This creates a visible jump in the graph. The third type is called an infinite discontinuity. This happens when the function values grow without bound near a point. In other words, one or both one-sided limits approach infinity or negative infinity. Graphically, this often appears as a vertical asymptote. So there are three main types of discontinuities. Removable discontinuity, which looks like a hole. Jump discontinuity, where the graph jumps between two values. Infinite discontinuity, where the function goes to infinity or negative infinity near a point. Recognizing these types will help us understand how functions behave near points where they're not continuous. Now, let's practice classifying discontinuities. Determine whether f of x is continuous at x equals 2. If it's not continuous, classify the discontinuity. F of x equals x squared minus 4 all over x minus 2. This is a rational function. A rational function is continuous everywhere except where the denominator equals 0. That means if x minus 2 equals 0, my function f of x will be not continuous. If x minus 2 equals 0, that means x equals 2. So f of x is not continuous at x equals 2. We determined that the function is not continuous at x equals 2. Now we need to classify the discontinuity as removable, jump, or infinite. In order to check to see if this is a removable discontinuity, we need to simplify the function f of x. So let's factor the numerator. In the numerator, I have x squared minus 4. This is the difference of squares. I'll factor this to x minus 2 times x plus 2. The denominator stays the same. From here, we'll cancel out the common factor and we'll end up with x plus 2. My discontinuity was at x equals 2, and after simplifying f of x, the discontinuity was removed. So this is a removable discontinuity. This means the graph of the function f of x behaves like the line y equals x plus 2, but the function is missing the point where x equals 2. This is the graph of f of x as the line y equals x plus 2 with an open hole at x equals 2. Now, let's look at another example. Determine whether f of x is continuous at x equals -1. If it's not continuous, classifying the discontinuity. F of x is x plus 2 all over x plus 1. This is also a rational function. A rational function is continuous everywhere except where the denominator equals 0. That means f of x is not continuous if x plus 1 equals 0. If x plus 1 equals 0, that means x equals -1. So the function f of x is not continuous at x equals -1. Now, we need to classify the discontinuity. And in order to check if the discontinuity is removable or not, we need to simplify the function. The numerator cannot be factored any further. The denominator cannot be factored any further. That means there's nothing to cancel out. So the discontinuity cannot be removed. Instead, the function approaches positive infinity or negative infinity near x equals -1, creating a vertical asymptote. Therefore, this is an infinite discontinuity. This is the graph of f of x. We'll have vertical asymptote at x equals -1. As x approaches -1 from the left, the function approaches negative infinity. As x approaches -1 from the right, the function approaches positive infinity. So, in these examples, we saw two different types of discontinuities. In example 6, the factor canceled and created a removable discontinuity, which appears as a hole in the graph. In example 7, the factor did not cancel and created a vertical asymptote or an infinite discontinuity.